Now here's a number that's a good number for you to know. I wrote it down in this way. Remember the numbers here. These are the key numbers. I'm going to be talking very shortly about the different kinds of radioactivity, including alpha, beta, and gamma. And alpha, you may remember, are these 2 protons and 2 neutrons. It's the helium nucleus, so it's charge 2. A beta turns out to be an electron, which has a charge of 1. Excuse me. A gamma turns out to be a high-energy particle of light. And in many ways will turn out to be the most dangerous of all of those 3. The most dangerous of all are the thing called fission fragments. But that's because of the way they're made and how they spread and what they do. So we'll talk about fission fragments too. But gammas are going to turn out to be the dangerous one. The gamma is the thing that comes out of this watch. But not out of my watch. These are just cosmic rays coming in. Cosmic rays are things coming from space. We'll talk about those too. But these are mostly gammas. Now, here are the numbers. You remember that 1 sievert equals 100 rem is the threshold for radiation sickness. Three sieverts is LD50. 50% will die within a few weeks. 10 sieverts, everybody dies usually within a few hours. 25 sieverts, which is 2,500 rem, is 1 cancer, whole body. Now, how much is a rem? Well, rem is 1% of a sievert. How much radiation does it take to give you a rem? Well, here's the number I want you to know. For 1 rem, what you need is 1 gigagamma per square centimeter. That means 1 billion gamma rays in every square centimeter. How many do we have here? Count them. So that was about 250. That's not a billion. That's not a billion, is it? So what? No big deal. I am nowhere near even a rem. Certainly not a rem whole body, just a rem right here. Not even anywhere near that. This is tiny. On the other hand, there are a lot of seconds in a year. If you wear this thing all the time, it begins to build up. You know, there are 100,000 seconds in a day, just about. No, there's 600,000. I have to work that out, something like that. There are 30 million seconds in a year, 37 million seconds in a year. So if you wear this all the time, it adds up, and that's what I don't want to do. The real deaths from these watches actually came from the people who made them. They had workers at the factory who would take the radium paint and paint it on the arms and on the letters. They were very skilled workers. And anybody here who's a painter knows that every now and then your brush gets sort of, ruffled, so you lick it. And so was tongue cancer. That became it was very concentrated radiation. It wasn't a whole body dose. It was just to the tongue. But it was such intense radiation. You didn't get radiation illness because it wasn't the whole body. But it was such intense radiation spread out over time so that there was a large number of tongue cancers among the painters. That's when they made this stuff illegal, when they realized what was going on. It would have been okay if they hadn't done that. But even so, they're now illegal. Bought this at a flea market. So look at this. 1 billion gammas per square centimeter is what it takes to get a rem. But you need 2,500 rem to get cancer. That's a lot of gammas. And so small exposures to small things like this really don't count for much. So that's this one here. Oh, in the book, do I say 2? What's that? Oh, that. Oh, then it's 2. I copied it correctly. So it's 2 billion gammas. Whatever the book says. If you remember 1 or 2, it doesn't matter. I want you to remember the billion. This is a physicist's way of thinking. Try to get the numbers in the right ballpark. That way you know what to be worried about and what not. Yeah, it's 2 billion. I have the number here. Now let's talk about this radiation. What is it? What are these things? We have this cloud chamber here, and let's see how this is doing. So remember how a cloud chamber works? Let's focus in on the cloud chamber, and I'll look at the projection up here. And I wonder if I could... So the cloud chamber works because the radioactive particle, in this case, the end of that needle, if you can you see the needle there? There's a needle sticking into this, and the camera's not showing it. It's very well. It's up there. Now the camera's not aimed, and I'm hesitant to move it. There's a needle there with beta rays coming out. Beta rays, turns out, are electrons. When the nucleus explodes, an electron comes shooting out. And it's up there, and every now and then you see a streak coming from it. But you get these other things, too, sometimes in the middle here. Those are cosmic radiations. These are things, and some of them are radioactivity from the wood. As you've read the chapter, you know we're all radioactive. We know wood is radioactive. All this stuff is radioactive. We'll be talking about that now. When these particles pass through the air, oh, that was a nice one, pass through the air, the water droplets tend to condense along the ions of the path. So we can see them when it happens. There was one right there. So this is what the cloud chamber does. Let's get one last really nice one. Come on. Little one there. Oh, that's a nice one. Then another one there. This is what's called ionizing radiation. So let's talk about the different kinds of radiation. It's a list of them, alpha, beta, gamma. The alpha turned out to be a helium nucleus. It's a very common particle that pops out, 2 protons and 2 neutrons, when you have a radioactive nucleus explode. And it happens in the ground from all the thorium and uranium that's down there. And when these particles come out, they're charged particles. They're positive protons on them. They attract electrons. They usually pick one up. They become a helium. The helium is now underground. It's a gas. It goes through the rock until it reaches something where it can't rise anymore. It gets trapped in the same place that oil gets trapped. Oil, which is a light liquid, tends to rise among the rocks. When it gets up there, this helium gets trapped. When people dig oil wells, this helium gas comes out. They used to throw it away. But when we run out of this oil, we're going to run out of this helium. And helium is very valuable, so it was made U.S. law that they're not allowed to throw it away. They have to bottle it. Some of it gets used for toy balloons. Other more important use is using it, I don't know, more important than giving toy balloons to little children. It's their introduction to physics in many ways. I'm not sure. But anyway, the secondary use is to use it for as a coolant, because it boils at a very low temperature. So if you make a liquid out of it, it stays cold. It will boil, but the liquid stays below the boiling point, and it's used for superconductivity. Its major technical use is to provide the coolant liquid for superconductors. Major use of helium. So we don't throw it away anymore. But that's what alpha particles are. Sometimes this is just an electron. It wasn't known for a long time. It's just an electron. Part of the reason it wasn't known is the beta rays were discovered before electrons were discovered. So how could they know it was something they hadn't discovered yet? Look, a beta ray. I think it's an electron. But sir, the electron hasn't been discovered yet. Oh, okay. Well, let's call it a beta ray. Gamma rays are something quite different. Now, both of these are charged particles. They have a charge. So when they shoot through matter, like a bullet going through matter, they have an electric charge, and if there's an atom nearby, the electron will be attracted to the alpha particle, or it'll be pushed away from the beta particle. But generally it gets knocked off its atom, and so you leave a trail of ions. Think of it like a trail of tears. It's a trail of ions. And these ions are basically broken up atoms, so there's a trail along the path of the particle where the damage is done. This is called ionizing radiation. You'll hear this term, ionizing radiation. So not only does it ionize, but it deposits energy along its path. And you measure that, and you tell how many REMs there are. Gammas are somewhat different. These are particles called photons, which are particles of light. They're actually wave packets. And we're going to be studying them a lot. Let me tell you a few things about photons right now. Suppose it's a very low energy photon. A very low energy photon, an example of that is a radio wave or a microwave. Radio waves and microwaves, the particle of light, it doesn't have any charge. And it's really low energy will even pass right through you, as radio waves will, as microwaves will. They'll pass right through you. Do they do any damage? Well, if they collide, I call these colliding particles, not ionizing, colliding. There is some probability that this particle of light, this photon, will hit an electron and knock that electron off, give its energy to the electron. Now what you've done is you've converted a photon into an ionizing particle, and you do the damage. So the damage is all secondary. So a photon, down here there's gamma rays. That's a very high energy. And that comes about from a lot of radioactivity. It gives gamma rays. A little bit higher is what's called the X-ray. X-rays are, some of it comes from radioactivity, but we can also get it from an X-ray machine. I have one here. This is an X-ray machine. We make X-rays. We can use this thing, make it work. I'll show that to you in a little while. These are all particles of light. In between here, we have infrared light. That's sometimes called heat radiation. If you have a heat lamp and you feel the heat radiation, that is infrared light, heat radiation. The fact that these are all just different energies of light is an amazing unification of physics. These things that behave so differently. We have visible light. That has energy of typically 2 electron volts per light particle. These have less. These have more. Then we have UV. That's sometimes called black light. Your sunglasses will often say UV safe. That means the UV from the sun will not get through that. UV light, we spend a chapter on these IR and UV lights because they're so important in physics. That's coming up after the midterm. And then higher energy or X-rays. So these are all particles of light. They have the same property. Some of them don't go very far. Visible light doesn't even penetrate your skin. It goes in a little way. If it's red, it might actually get through a little bit of skin. Whereas X-rays go through your skin but not the bone. So they have different properties, and it all has to do with their energy. Right now, let's look at X-rays and gamma rays. These are things that are very energetic bundles. When they pass through you, they mostly pass through you. When they hit an electron, they knock it off and they give the electron a lot of energy. That electron is then ionizing radiation and causes damage. Now, why am I making a big fuss about gamma rays? The reason is they get deep into your body. They can penetrate walls. they can go through half a centimeter of lead. That doesn't seem like enough, but lead is actually pretty heavy stuff. So the gamma rays are penetrating. And that's their key feature, is that they're penetrating. I was working on a study just last week about what to do if a nuclear explosion goes off in San Francisco and the radiation that comes over Berkeley. What do we do here in Berkeley? You know, and there are two obvious options. One is evacuate, and the other obvious action is go indoors. Go indoors, the radiation lands on your roof. You're fairly far removed from it. The radiation has to reach you in order to do any damage. And then it turns out the radiation only lasts for about a day. We'll be coming to that. So this is what I call the difference between ionizing and colliding radiation. Of these key radiations, they're all one or the other. Microwaves, where are those on this list? Well, they were here, microwaves. People talk about microwave radiation. And here's the scoop on microwave radiation. From cell phones, from your microwave oven. This is something you should really know. You look in the history of this. Why are people so afraid of this? I believe the answer is because it has the word radiation attached to it. What about heat radiation? Don't we worry about cancer from heat radiation? People don't seem to worry about that, but cancer from microwave radiations is just about as remote as that. The fact is that the studies that have been done, there is no known mechanism whereby microwave radiation can induce cancer. Nobody has been able to imagine how microwave radiation could induce. Does that mean it doesn't happen? No. Okay, so you've got to keep on doing your studies. In the meantime, I'm going to scare people by telling them, watch out for the microwave, you know, with their cell phones. And then I'll say, and guess what? Here's a guy who was using a cell phone and he got brain cancer. See? So the studies are done. There's no significant effect. Nobody can, for most cancers like radiation, we know the mechanism. Ionizing radiation goes through, destroys the DNA, mutates it, and causes cancer. We understand that. Microwave radiation comes through, and it's absorbed on an electron. The electron gets a minuscule amount of energy, and for the most part doesn't even leave the atom. It just heats it up a little bit. The only known things that microwaves do is they heat you up a little bit, which is why we use microwave ovens. You don't want to put your cat in a microwave oven to dry it out. The reason is it heats up everything, and some parts of the body, and particularly the eye, usually don't generate heat. We don't have blood vessels deep in the inside of the eye. You heat up the eye, it has no way of getting rid of the heat. It is not good. So heating can be bad. The microwave oven was discovered, invented by an engineer when they had a big radar set, and he discovered that the soldiers were standing in front of it on a cold day to warm up. He said, oh, of course, microwaves will heat things. And then you make a little box with metal things in it so the microwaves don't get out, and you can put something in there and it'll heat. You don't want to have metal on the inside because it turns out, as we'll be discussing, that microwaves cause large currents to flow in metal. You don't want that. You just want the electrons, the individual electrons, not to flow large distances when they can cause sparks, but just to move around inside of the atoms and warm up. But microwave, I mean, this is one of the greatest urban legends of the current era, that microwaves cause cancer. Don't use these microwave things. There's no basis in anything to back that up other than the fact that it has the word radiation associated with it. What does the word radiation mean? It means radiates, which means travels from here to there. So light is radiation. Infrared is heat radiation. Gamma rays are radiation. Now, gamma rays do something different. When a gamma ray enters your body, it knocks an electron. But because the gamma ray has a huge amount of energy, typically 1,000,000 electron volts, rather than a fraction of an electron volt like microwaves, tiny fraction of electron volt, millions of electrons, that's enough to knock the electron out. It then becomes ionizing radiation deep within the body. It can cause cancer. So gamma rays are one of the greatest dangers because of their long range. Alpha particles, these helium nuclei, they come out with typically 1,000,000 electron volts of energy. But as you saw last time, they're stopped by a piece of cardboard. What happens if I take a strong alpha source and put my skin on it? The answer is, my skin warms up a little bit. Doesn't it kill the cells? Well, it turns out the cells on the surface of the skin are already dead. So the general consensus is alpha rays cause no harm in the environment unless you breathe them in. If you digest them and they get into the, your digestive system, they can do a little bit of harm, although not a whole lot, because most of the stuff will just go right on out. You don't want to get it into your blood, you don't want to get it into your lungs, because your lungs don't have that dead layer. So the biggest danger from alpha particles are breathing them in. This has led to a big controversy about the dangers of plutonium. Because it turns out plutonium, hey, you make a bomb out of it, that's bad. Yeah, but there's an urban legend that is the most dangerous substance known to man. It turns out to be significantly less poisonous than botulism, which is the toxin you get in bad mayonnaise. But nonetheless, there's this urban legend that it's the most dangerous material known to man, woman too, and they're both wrong. I have a film clip of Walter Cronkite, the most trusted man in America of his era, the great newscaster, saying after 3 Mile Island, plutonium is the most dangerous substance known to man. And it isn't, that's just wrong. But again, it's one of these urban legends that spreads. Plutonium has the following danger. If you could divide it up into 5 micron-sized particles and then breathe it in, it would in fact be more dangerous than botulism. I'm sorry, than anthrax. It's worse than anthrax if you divide it up into anthrax-sized pieces and then breathe them in. Now, in the anthrax attack in 2001 in New York City, the anthrax did not get divided up into the right size pieces. That's why there were so few deaths. There were 5 people killed, mostly elderly, a few younger people, but mostly the anthrax didn't get divided up, and so it doesn't get into the inner part of the lungs. What about plutonium? Will that divide up into 5 micron sized pieces? So people at Livermore have done extensive experiments where they blow up some plutonium and see what size particles come out, and it never turns out to be these 5 micron sized pieces. So why do we worry? Because people say you cannot trust Livermore in Los Alamos. They're trying to prove that plutonium is not dangerous. Well, I know the people there. They're not trying to prove that. They wanted to find out so we could take the right action. They say make a terrorist bomb out of plutonium, and even if it doesn't work, it spreads plutonium. Well, in my mind, if it doesn't work, it spreads plutonium, and that spreads irrational fear. Plutonium doesn't form these micron-sized particles, which would make them more dangerous than anthrax. But I'll tell you, if I were advising the terrorists, and I've read all your bios, I believe them all. I don't think we have a single person here who is actually a terrorist taking this course for that purpose. You may have friends who are, so be careful what you tell them. This is being webcast. Don't. You terrorists out there, ignore this. The fact is, if you really want to kill people, use anthrax, not plutonium. And besides, it's a lot easier to make. It makes itself in the right conditions. Plutonium doesn't. If you have some plutonium and you have the right isotope, plutonium-239, use it to make a bomb. Don't waste it trying to kill people with little micron particles you can't get. So that's an important thing to know. And when plutonium was used recently in the flight to Pluto, which was launched just a few weeks ago, I saw some blogs of people who were outraged that the issue of the dangers of plutonium are no longer being discussed. And in fact, my reaction was, what a delightful advancement in American consciousness that we're no longer having great outrage over this harmless stuff being launched to power a satellite on a mission that will tell us wonderful things about the outer solar system. So those are my thoughts on plutonium. There's a lot more in the textbook about plutonium. Microwaves and plutonium. So I'm running through the list of different kinds of radioactivity. But let me take a break from that and talk about this half-life rule, which is purely a quantum mechanical effect. And so here we are getting into the heart of quantum mechanics with the half-life rule. That's the following way. I am older than most of you. I will outlive some of you, but most of you will outlive me. The fact is, as I get older, my life expectancy gets shorter and shorter. I'm now 62 years old, and my life expectancy is probably another 20, 25 years. for someone who is, so that, I'm getting older. The remarkable thing about radioactivity is it doesn't work that way. When an atom is sitting around waiting to explode, boom, it's gone. Suppose you create a large number of atoms. Suppose you make plutonium, and you have this plutonium here, and you wait. And after about 24,000 years, half of the plutonium would have exploded. And you have this half left. So is it now the old man? Is it something with not much life left? So you make some new plutonium, and you compare it to the old plutonium. And they behave identically. This one isn't aged. In another 24,000 years, half of it will decay, half of this will decay. And you take the part that's left, 1/4 of the original. And it behaves like brand new plutonium. This stuff doesn't age. So what is going on here? The fact is, what's going on here is so mysterious that we just think of it as a new law of physics. It's not something you explain in terms of other things. There's no mechanism inside that's click, tick, 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 ticking. What happens is if you have an atom of plutonium or uranium or potassium-40 or carbon-14, it has some probability of decaying every second. And that doesn't change. For carbon-14, after 5,730 years, the probability that it would have exploded is 50%. That's called the half-life. But if it hasn't exploded, it's not going to then explode in the next 5,000 years. It only has a 50% probability of exploding. This is truly mysterious and amazing. And nobody has been able to explain this in terms of anything else, and most people have given up trying. This is the way the world of quantum mechanics works. It's a probabilistic thing. So if you start off with 1028 atoms, on the average, after one half-life, it'd be down to half of that, to 512. If you wait another half-life, you're down to 256 on average. Sometimes it'll be more, sometimes less. It's a square root rule there. You wait another half-life, and it's down to 128 on the average. And you wait another half-life, and it goes half, 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 half. Now, after about, I don't know, maybe after about 60 half-lives, even if you start off with Avogadro's number, 6 times 10 to the 23rd, and then you're down to 3 times 10 to the 23rd, and then 1.5 times 10 to the 23rd, and you do that. But if you do that for 60 half-lives, you're down to 1. Now, what happens when you have 1? Will it decay or won't it? It's only a probability. This is really strange. It's not as if there's something in there, a little clock that tells it. It's not like I'm using up my, all of my energy and eventually run out and my cells are slowly dying. There's nothing like that going on. These old particles are identical to the new particles. And we have ways of measuring identical by doing a thing called an interference measurement. And it's very, very strange. We'll talk a lot more about this as we get to quantum mechanics, but this is a real quantum mechanical effect. And not only is it not understood, but most people think we never will understand it, because this is the fundamental principle of quantum mechanics. This is the principle on which everything else is based. And when you start with a first principle, you don't explain it in terms of something else. You try to explain it in terms of a little mechanical thing going inside the nucleus. There aren't any mechanical things going inside the nucleus. Things don't work with little mechanical tools down at that level. Things work quantum mechanically with wave functions down at that level. And this is a fundamental property of wave functions, so we're never going to understand it. Very strange, the half-life rule. You take two particles which are truly identical, and they decay at different times. Now, one of the things that I find fascinating about this is if two things, this is an absence of causality. These two things are identical. They're treated in every way. They're produced together. They're identical twins in the identical environment, and they will decay at different times. So the decay is not causal. You can still say something about it. You say, oh, it's very likely it will decay within a few half-lives. So we have a principle that allows us to discuss the statistics, but not the individual cases. Now, back in the 1800s, people, when physics was really going strong, they used physics as an example of how we are probably just chemicals that are reacting to input. And if we could write down all the equations of the body, we would be able to predict whether I'm going to hit the table with my hand or not. Okay? And that's predictable if you really knew all the atoms and how they were moving and so on. Now, that was based on the fact that physics looked causal. And hey, maybe our own free will is just a big illusion, which to a large part it is, as I've learned. The things I pick on my own, I then later figure out who influenced me to do that. So we do have some illusion of free will. But do we have no free will? People used to take from physics that everything is causal, and therefore free will could be an illusion. And many people who saw all the power of physics, hey, all the things you can make out of it, you know, steam engines and later atomic bombs. Physics seems to work better than religion, so let's take on physics as our new religion, believe that this is what everything is. And then, with the discovery of radioactivity and with the discoveries of quantum mechanics, the basic assumption that was used in that logic is totally wrong. Physics is not causal. There are major things that happen like radioactive decay, and at the atomic level, many things behave in this way. You can only talk about probabilities. There is no causality here. So what has been demolished was the 19th century argument against free will. Does that mean we have free will? No. It just means that the one powerful argument against it is completely demolished. This is something that a little bit of physics relating to other subjects that I think everybody should know. So that's the half-life rule. We're going to find next week that there's something opposite, the doubling rule. If you double, you can go from one atom to 2, 4, 8, 6, and 32, 64, 128, 256, and so on up, and get up to Avogadro's number in about 60 to 80 doubling times. And that's the basis of the chain reaction, which is used for everything from the atomic explosion to PCR in biology, which is what's probably the most important invention in modern biology, is PCR, the polymerase chain reaction that allows us to measure DNA very conveniently. So this chain reaction is the doubling rule, getting from small numbers to very big ones. The opposite is the half-life rule, where the numbers get down. You know, after the probability of surviving one half-life is 1/2. The probability of surviving 2, multiply that by 1/2. Of 3, multiply that by 1/2. 4, multiply that by 1/2. Generally, it's 1 over 2 to the n, where n is the number of half-lives. And that number can get small very quickly. You don't believe it? Multiply 0.5 by itself on your computer or calculator or spreadsheet and just see how small it goes. So pretty soon, the probability is this thing will have decayed. You're not going to have something around 30 half-lives later. It's really gone. So it doesn't have free will. Well, except on little decisions. Something like that. So I talked about ionizing and colliding. Of these radiations, electrons, helium nuclei and helium balloons, gamma rays, these are penetrating. X-rays are also penetrating. They're not quite as energetic. They are 1,000 electron volts, where gamma, these are like 1,000, where these are like 1,000,000. We can make an X-ray in an interesting way. What you do is you take an electron, an energetic electron. This is how you make an X-ray. You take an energetic electron with maybe 20,000 electron volts of energy. That's 20,000 times as much as a typical atom has. To give it this energy, you have to use electricity, and we'll talk about that after the midterm. But you get this thing going really fast, and then you run it into a piece of tungsten or other heavy metal. When it gets to the tungsten, this electron will stop very suddenly because of the nuclei in the tungsten have very positive charge, and they will get this thing and they'll grab it. When you suddenly change the velocity of an electron, it tends to emit a gamma ray. So the gamma rays will come out like this. You're basically shaking the electron. We'll talk a lot more about this when we get to radio waves. And so the gamma ray comes out like this. It's not a gamma ray, it's an X-ray. Because it will have an energy typical to this, generally a little bit smaller, maybe 10,000 electron volts. Remember, visible light has an energy of about 2 electron volts. This is 10,000. This is still light, but it behaves very differently. When it passes through you, it has so much energy that it tends not to be stopped by conductors. It gets right through, gets stopped by calcium, making a shadow. When you're getting a tooth x-ray, what they do is they put your tooth here. So here's your tooth. And you put a piece of film behind it. And here's the calcium, here you have the hard parts and so on. And you get a shadow picture of the tooth. And if there are places where some of the tooth is decayed, then a few more x-rays come through. Because there's a few more x-rays coming through, it exposes the film more and makes a dark spot. And the dentist is trained to look for these little dark spots in the kind of pattern that they expect for these dental caries, or as I like to call them, dental cavities. And they see these dark spots on the x-ray. But you're looking at a shadow of the tooth made with x-rays. And this is the big dental device that they put up to your tooth. They stick this piece of film behind your tooth. I believe the dentists have special designers at the dental companies that have managed to figure out how to make film in such a way that it maximizes the discomfort of the person who has it in their mouth. I don't know how they do this, but with all this modern technology that's being developed, and better x-rays, and they put all this stuff on me to make sure there's no x-rays going to my thyroid, and so on. And then they stick this piece of cardboard in there, and they say, okay, now close the mouth and wedge it with your gums on the edges. Yeah! And then, anyway. That's how we have a little x-ray device here. Here's one of these tubes. The electrons come off. They're accelerated this way. They hit that little piece of tungsten. The x-rays then shoot out from the side of the tungsten, in this case against the wood. So if I put this in here, we can actually make it work. It's not a very bright tube. We have to buy a better tube. This one is wearing out. It doesn't produce as many electrons as it used to. And it's cleverly done, just like the dental assistant has to leave the room to turn on the switch so only you get irradiated. That's because you get radiated once every few years, and she gets irradiated every day. So it will not turn on until I close it. And now I can turn it on. We have a little bear here. And let's turn on this tube. We can turn the lights down. I'll turn on the x-ray tube. And maybe we'll be able to see it. We're going to get a new x-ray tube because this thing is getting so dim. We really have to turn the lights off. Really turn the lights off. In fact, I'll even turn this light off. Oh, for alcohol to be legal, its radioactivity must be above a certain limit. We'll talk more about that. That's so contradictory, that's a great exam question because you wouldn't expect it. So do we see it glowing at all? Yeah, look at that glow. Okay. Impressive. Let's put the bear in there and see if we can see the shadow. This is designed with interlock, so as soon as I lift this thing up, it turns off. I can see it. I can see the electrons in there a little bit. So let's see if they turn off when I lift this up. They do. It's turned off. Stick the bear in there. We'll see if we can see an x-ray of the bear. I don't know if this will work or not. Almost decided not to show this thing because, hey, you guys have all seen x-rays. But this one illustrates the tube, and the thing is turned on now. This is lead glass. We got a flash there for a moment. I don't know if you saw it. The x-ray tube suddenly got a strong beam of electrons. And, oh, we're getting arcing here. I see the problem. Okay. The arcing, we move this thing, get this wire out of the way. Get this thing out of over there. And now let's see if that works better. Now getting arcing there. These things are a little bit of a pain. I was advised I should use short wire so I wouldn't have this problem. How are we doing? Okay, I've got to get a better tube. Let's forget this and put the light back on. The key thing here is that the gamma ray, the X-rays, are stopped by the heavy elements. The heavy elements are the one near the end of the periodic table. It turns out calcium is heavy enough, even though it's not very heavy. If you look at that chart, it's far enough down on the table that the calcium in your bones tends to stop the signal. Can't find my laser pointer. And so there's more absorption by the calcium than there is by the soft tissue. And that makes the shadow of the calcium. When they were first discovered by Röntgen, it was a fantastic discovery that you could get shadows of bones, so you could actually see a broken bone inside the body. People thought it was a fraud. You could look up the history of Röntgen and his discovery, and everybody believed this was a fraud. But it really was true. So within a few weeks, people caught on. Every now and then you'll see something in the newspaper where someone has some great discovery. About half of those turn out to be false in the long run. Why are they then in the newspapers? Answer: because they're good news. You should be aware of this. Be aware of the fact that great discoveries announced, particularly stupendous ones. There's one just a few days ago about someone who manages to get energy out of ordinary water by using a transition that violates quantum mechanics, so quantum mechanics must be wrong. And I look at this, and I've seen dozens of these things in the last 2 years. I've seen them my whole life. These things come out, and they get the attraction of the newspaper reporter, because the newspaper reporter says, it's not my position to judge this. It's a controversy. So if it's a controversy, and especially if the establishment claims this is nonsense, that's an even better controversy. So these things get reported in the news. Be on the lookout for them. A lot of you send me things like this and say, is this for real? And most of them turn out not to be. I say, no, it's pretty obviously a fake. And here are the suspicious things that make into a fake. The way it was reported, the test they reported, the fact that they can't tell you all the facts because it's super secret and they have patents pending, and all that kind of stuff is always there on these fake things. So I discussed the half-life rule. Half-life rule makes for some fascinating things, particularly Bill Libby, back in the 1950s, when he discovered there was a radioactive form of carbon, and that this radioactive form of carbon, we're made out of carbon. Not only that, but this carbon is produced in the atmosphere. So cosmic rays, that's radiation from space, that's what the CRs are, cosmic rays. Do I have a list of radiation here? Cosmic rays. Radiation from space, we think from exploding stars, actually. From radioactivity of exploding stars, these cosmic rays come in. They make the atmosphere slightly radioactive. One of the key things they do is they collide with nitrogen-14, and they make something called carbon-14, or radiocarbon. Carbon-14 is also called radiocarbon. And it's made in the atmosphere. Radiocarbon. It's made in the atmosphere by cosmic rays. And then it decays with a half-life of about 6,000 years. So you think it would go away, except it's always being made. And so it's being made at a certain rate, and it decays at a certain rate. The result is the amount in the atmosphere stays approximately constant. Only approximately constant. But it's fairly constant. Assume for this course that it stays constant. Now here are we. And there are the plants. And where do the plants get their carbon? They do it from carbon dioxide in the atmosphere. So plants take in radioactive carbon. What fraction of the carbon is radioactive? 1 part in a trillion. That's 1 part in 10 to the 12th. 10 to the minus 12 of carbon is carbon-14. No, that's not an important number for you to know. But it means but that's almost undetectable, such a tiny part. It's not undetectable because when it decays, it emits a beta particle, an electron, that comes streaming out. So even if you have very little of this stuff, you can take a radiation detector and you can detect the radiation. So you can detect radioactive particles even though they're a tiny constituent. Now think about this. There's 1 part in 10 to the 12th in the atmosphere of carbon. It's carbon-12. Plants get all of their carbon from the atmosphere, not from the soil. They get it from the atmosphere by breathing in carbon dioxide. They make carbohydrates out of it. So they're carbohydrates. Hey, if they last for 6,000 years, half of it will be gone. But most of them are eaten or decay within a few years. So they have all of their radioactive carbon in them. So plants are radioactive. If they get buried underground in oil, then a half-life later, they have a half, and another 6,000 years, half of that. And after they're there for a few million years, nothing left. So oil is not radioactive. If you make alcohol out of oil, you can tell it was made out of oil because it's not radioactive. It was made out of grain. It's radioactive. The U.S. Department of Agriculture and the U.S. government has decided to make it illegal to make drinking alcohol out of oil. As near as I can tell, the logical reason behind this is that it would be so cheap if you made it out of oil that people would start buying that instead of paying for grain alcohol, which is made out of plants. So to protect the alcohol industry, they make it illegal to drink alcohol that's made out of oil. That's the only logic that I can find in this. So they're basically trying to benefit an industry. Leave it to you to decide whether that's good or bad. But the plants are radioactive. If you eat plants, you're radioactive. About the same level of carbon, 10 to the minus 12. If you eat animals that eat plants, you're radioactive. I know of nobody who isn't radioactive. Once you die, your radioactivity is no longer part in 10 to the 12, 10 to the minus 12. Once you die and have been buried for 6,000 years, your radioactivity is half of that. Because now you're no longer eating. And so when you find a buried bone, you can measure the radioactivity in the bone and tell how long ago it stopped eating. And that's called radiocarbon dating. One of the most useful things. Libby got a Nobel Prize for that. I actually spent a lot of my research on radioactive carbon dating. I invented a method called accelerated mass spectrometry, which is 1,000 times more sensitive way of measuring it. And I'm happy to report these days that almost all measurements being done of radiocarbon dating are done using the Muller method. So that's a rather proud achievement of mine. My idea was simple. You don't wait for it to decay. You go in there and you count the carbon-14s. Hey, that's hard. There's so few of them. Okay, but there are other ways of doing it than looking for the radioactivity. And there are so many of them in there. Since if you wait a year, only 1/6,000th of them decay. So go in there and count them all real quick, and you do much, much better. And I came up with a way of doing that. So that's one of my claims to fame. Potassium-argon dating is a little bit different. But again, it's based on the natural radioactivity. Why are only a few things radioactive? That's an interesting story, too. It's in the book. When the universe was created, when the solar system was created, almost all atoms were radioactive. Almost all. The ones that were radioactive are long since gone. We're left with that tiny little fraction, that tiny little subset of atoms that aren't radioactive. Everything used to be radioactive. In the early solar system, everything was radioactive. And now it's all disappeared. We are the ashes. Ashes of a supernova explosion, which produced mostly radioactive things. We're the few things that are left. Like when uranium explodes, out comes this alpha particle. The alpha particle is not radioactive. It hangs around. The uranium's gone. Uranium has a half-life of uranium-235 of 1 billion years. That's why it's mostly gone. So potassium-argon dating is particularly important in geology. And this is what happens. When potassium-40, still haven't found my laser. It's sitting here somewhere, I'm sure. Anybody see it? Okay, we'll find it. When potassium decays, it converts. No, not there. Okay, when potassium-40 decays, it emits an electron. The electron comes out of the nucleus. That means the nucleus gains one charge, and you go from being potassium to being argon. So potassium-40 changes to argon. Now, argon is a gas. So here we have a nucleus exploding, emitting an electron, that's all. As a result, the nucleus now has more charge to it, and so it's a different element. But this element tends to be a gas. So here's the way potassium-argon dating works. You take a rock, and you take, maybe you have a volcano. And this liquid stuff comes. It doesn't have any gas in it because it's so hot, all the gas boils off. So it has no argon in it. Then this rock cools and becomes a solid rock. And the question is, when did that happen? How long ago? Well, it has potassium in it. Most rocks do. Some have more, some have less. You measure how much potassium is in there. That potassium is about a part in 1,000 of potassium-40. So there's a little bit of potassium-40 in there. If that rock just became rock, then you look and you'll see there's potassium-40 and there's no argon gas because that all boiled off. But if you wait 1 billion years, you'll find half of that potassium has turned into argon gas. and that gas is trapped within the rock. So if you measure how much argon is trapped within the rock, you know that rock was formed 1 billion years ago. Maybe if only a little bit is trapped in the rock, it was formed 1 million years ago. This is the primary way we have of telling when a rock was formed. When we say the age of a rock, what we mean is when did it become solid? When did it start accumulating argon? So this is really a very different thing than carbon-14. In carbon-14, we are eating radioactive carbon, and when we die, it starts going away. For rock, what's happened is it has some potassium in it. The potassium is producing argon. Argon's not radioactive. It's that this is radioactive. The radioactive thing goes away. You're left with things that aren't radioactive. And that way you can tell what the age is. Now, just one last thing in today's lecture that I want to touch on quickly is fission, fusion, and neutron activation. When alpha particles, helium nuclei, or electrons pass through your body, they do damage, but they don't make you radioactive. When a gamma ray comes into you and knocks off an electron, which then damages your DNA, you might get cancer, but you don't become radioactive. Radiation doesn't make you radioactive, with one major exception. And that's neutrons. A neutron is like a proton without charge. Helium has 2 neutrons in it. Carbon, the nucleus has 6 protons and 6 neutrons. These are just like protons, except they have no charge. They have nuclear glue, but they have no charge. What makes something radioactive? It's those balance of nuclear forces. And sometimes, if you add a neutron to a nucleus, it changes the balance of nuclear forces in just the right ways to make it radioactive. That's called neutron activation. All you need is a supply of neutrons. Where do you get neutrons from? Well, the main place you get them these days are, there are lots of different places you can get them. We'll talk about those next week. But they can make other things radioactive. Frank Asaro, who found the iridium that led to the discovery of what killed the dinosaurs, doing this at the suggestion of Louis and Walter Alvarez. He used neutron activation. What he did is he took this little bit of clay and hit it with lots of neutrons. The iridium became radioactive. Then he could detect the radioactivity. But there's one truly frightening kind of, this is called induced radioactivity. And that's if you set a neutron hitting uranium-235 or plutonium-239. If a neutron hits one of those, then the atom breaks apart to what's called fission with a release of 200 MeV per nucleus. 200 MeV. But now here's the really key thing. When it does that, not only does it release these fission fragments coming out, both of which are usually radioactive, because most things that are created are radioactive, so the fission fragments become the most dangerous kind of radioactivity, the fission fragments. But in addition to that, typically 2 or 3 neutrons come out. Now, the big deal about that is you have 2 or 3 neutrons that can go fission another nucleus. Let's say it's 2. In the first generation, you get 1, and in the second generation, 2. And then those go out in fission, you get 4, 8, 16, 32, 64. After about 70 generations, you have exploded every nucleus in the core of your nuclear bomb. And it's called a chain reaction. So next week, chain reactions.